Welcome to the sixth lecture of parallel algorithms. Today I would like to discuss sorting networks, and I would like to deal with three types of them. And the most important topic of today is a technique to prove sorting networks to be correct. And we will give, first of all, the technique, and then some applications of the technique to these networks. That I will do, of course, after I've checked that everything is okay with you. So, if there are any problems with the previous lectures or with the assignments, then please tell me so. Then we can discuss them before we deal with these new topics. So are there any problems with the lectures, imperatives, problems with the assignments? Everything okay? Okay. Then we start with our new topic. So as promised, I will deal with sorting networks. We will first discuss the basic principles underlying sorting networks and the complexity of them. Then I will deal with insertion networks and try to convince you that there are some design principles behind these sorting networks that enable you to construct them in an inductive way. So assuming that you have a network that's capable of sorting n inputs, you can build one that is capable of dealing with n plus 1 inputs. Then, after discussing an insertion sorting network, so based on one of the most simple principles of sorting that we dealt with in our bachelor course on sorting algorithms, we will introduce a technique called the 0-1 principle that enables you to prove a sorting network to be correct for all inputs by just concentrating on binary inputs. So we can show that a sorting network can deal with all kinds of numbers and is correct just by proving that it sorts binary vectors in a correct way. Then we treat parallel merge networks, and we show how you can merge two already sorted vectors into one large sorted vector. And after discussing that, we will discuss a variant of such a network using the same design principle as I told you before, by using it to sort the vector. So, given the fact that you have a merging network, how can you design a network that's capable of sorting? And then finally, and that's the most difficult part, we will deal with bitonic sorting networks. So, assume that you have a vector that is nearly sorted. That means that you have a vector that consists of two halves, one half that is sorted in an increasing way and another half that's sorted in a decreasing way. So these are sequences that have one peak, are unimodal. Once you have two of them, we can show you how to achieve a new bitonic sequence as a kind of merge byte. And then, in the same way as we dealt with parallel merge networks, I will show you how we can build a sorting network that's capable of sorting in a bitonic way. So given an arbitrary vector, how to transform it into a series of bitonic vectors, and then using the kind of merging principle to obtain a bitonic sorting network. For all of them, of course, we will give the corresponding complexity measures. So that's the topic for today, and let's just start with a sorting network. So why do we need to concentrate on sorting networks? Well, maybe you remember that in previous lectures we said, well, there is one typical model for sorting that uses only comparators. Well, taking that very seriously, you could imagine that you just concentrate on a piece of hardware that's capable of just doing that, making comparisons between numeric inputs and just sorting two inputs, giving the minimum and giving the maximum of those two numbers. Well, that exactly is what we will try to do. So given two inputs, x1 and x2, we want to find the minimum of x1 and x2 on one output line and the maximum of x1 and x2 on the second input line. And to indicate that we have applied here a comparator, we put an arrow between those two lines, that connect x1 with the output and x2 with the output. So the minimum of the two numbers here appears at the first output line and the maximum of the two at the second. So a network based on these wires and comparators is called a sorting network. Well, just to give you here an example, suppose that here we have such a network and now we have 4 inputs, and we would like to show you what the output is, and hopefully the output will be a sorted variant of these numbers. So what happens? Well, if you compare 5 and 9 here, this case, then of course the minimum will appear at the upper and the minimum at the lower output line. Now comparing 9 and 6 here with the second comparator, then 6 will appear here at this output line and 9 at that output line. Then of course again 4 and 9, 4 will appear here, 9 will appear there. Then going onwards, well, with respect to this comparator, no change can be observed. 4 and 6 are compared, 4 appears here, 6 appears there, and then comparing 4 and 5, 4 appears here, 5 appears there, then there is no comparator in between this line and the output, so 6 appears here and 9 appears there. So the output indeed is 4, 5, 6, 9. This is a very simple application of a sorting network. So what's the difference between a sorting network and a sorting algorithm? In principle, well, the sorting network, of course, is capable of only dealing with inputs up to a certain finite number of inputs. So here up to 4. And of course an algorithm should deal with an arbitrary number, but you can build, of course, these networks for arbitrary number of inputs. Okay. If you would like to design such a network, then it's important that you make a distinction between the amount of hardware that you need to build it and the speed you can achieve in sorting. So the amount of hardware, of course, is rather simple to determine. The amount of hardware is simply the number of comparators that you need in this network. So the size of the network is the total number of comparators. Now imagine that you have a sequential algorithm that would simulate this network. Then the complexity of all the operations is determined by the total number of comparisons you have to make. Yeah? So the sequential complexity of this sorting network is similar to the total number of comparators, and that's what we have called time or number or the amount of work, yeah, of your algorithm. The depth of the network, that's the maximum number of comparators that appear on a given input-output path. So you walk through the sorting network and you determine the path that has the most comparators on its path. And that's, of course, determining the time that you need to perform sorting. Okay, well, of course, in this circuit, it is not difficult to come up with the size. That's simply the total number of comparators that's present in this network. And if we would like to determine the depth of the network, well, we have to find a path where the maximum number of comparators is present. Well, this is such a path. Count here the number of comparisons. This is comparison number 1, comparison number 2, comparison number 3, 4, 5. Yeah? And there is no path that has more comparators. Yeah. So it is not the number of comparators that here on between two paths, it is simply counting the endpoints of comparators that appear on such a path. So the number of comparators that are touching the path. So the depth of this circuit is 5. And of course, yeah, what you would like to know is, well, how costly is it to build such networks? So what's the amount of hardware that we need in order to build sorting networks, and what is the speed that we can achieve? And so we would like to minimize both the size and the depth of such networks. Okay. We will deal with 3 variants of those networks, and we will start with a very naive insertion sorting network, and that's meant to illustrate the design principle that we have in mind. So I told you, we simply start from, well, assuming that we know how you can deal with n inputs, and then we build on the basis of a certain principle, here for example the insertion sorting principle, how we can extend it to n plus 1 inputs. Then we deal with parallel merge networks, and finally with binomial sorting networks. So let's start with insertion sorting networks. So I assume that we already know how we can build a sorting network that is capable of sorting n inputs. And now I will construct Sn plus 1 from Sn. So in a kind of inductive way, we will build these networks, and then we get a feeling how to construct. So assume that you have an insertion sorting network that's capable of dealing with n inputs. And now here the n plus 1th input comes. What's the intuitive idea for insertion sorting? Well, if you have an already sorted number of inputs and you add a new input, then you have to compare your new input with every input that's already sorted to determine the place where you have to put your new input in. So, well, in terms of this sorting network, that's very easy. You just compare your new input with every input that is appearing here on the output of this sorting network. So in principle, the right place of your new input could be, of course, this place, that place, that place, that place, until the first place. Okay. Now, looking at this picture, it is not difficult to imagine how you can build the whole network from this principle, because, well, here this staircase appears, of course, is in Sn2, and is simply repeated for the first n minus 1, n minus 2, etc. So, well, if we take now our network Sn plus 1, then Sn plus 1 contains, of course, this part of the circuit and the circuit that belongs to an S. So what's the size of this network? Well, if you would like to build such a network that's capable of dealing with n+1 inputs, you have to provide at least n comparators, and you have to provide, of course, an Sn network. So the size of Sn+1 is the size of Sn plus n. Well, this is a linear recurrence that you can easily solve, and there the amount of hardware is that you need to build such an insertion network. The depth of Sn+1 equals the depth of Sn+2. Why? Well, imagine that you have here a certain output line. Yeah. What is the maximum number of comparators that are touching a path additional, so above the number that appears in Sn? Well, here we have the number in Sn, and take here an output line, and you see that two comparators are touching such an output line. Take an arbitrary, and you see that for every output line it adds two additional comparators touching. So that means that the depth of Sn+1 equals the depth of Sn+2. From these two, you can immediately determine what the order is of the amount of hardware that you need. The order of the amount of hardware is n squared for Sn, and the depth is the O of n for Sn. So more in particular, we have the size of Sn is half n times n-1, and 2n minus 1 for the depth. Okay. Now we have an important problem. We can determine, of course, now the amount of hardware, and we can determine the speed, in principle, of our network. But how would we prove our network to be correct? And that could be a big problem. Because, well, the answer to your simple question, how do we know that the sorting network Sn that we just constructed is correct, should be we have to show that every input vector x of length n results in an output vector y that's a sorted variant of x, but we have a major problem here. There are infinitely many of those input vectors, and we would have to check them each to prove our network to be correct. Well, if you have a proof that is infinite, that's, well, not a real proof. So you have to prove it in a finite way. Well, how to solve it, this problem? And that's where our 0-1 principle comes in. What we are able to do is the following. We are able to show that the sorting network is correct for arbitrary inputs if we can show it to be correct for all binary input vectors. But that's a major achievement, of course, because instead of an infinite number of inputs, now we have reduced the proof to a finite number of inputs, because now we have only to check 2 to the power n binary inputs, and that's a finite number. And so in principle, we could prove just by checking each input vector that our sorting network is correct. Well, how to prove that? We should first use a kind of lemma. So the lemma is a helper for proving some major result, for proving a theorem. And this lemma says that, well, if you have a sorting network, S, and you apply it to an input vector x containing n inputs, and you achieve an output y1, y2, yn, and you have a function that's monotonically non-decreasing. So if you have two numbers x and y, and x is not larger than y, then the same holds for fx with respect to the f of y. If that's the case, then you don't need to sort fx1, fx2, fx1 if you know what the output is of sx1, xn, because you immediately know the results. You can retrieve the results from the result for x1 to xn by just applying f to the outputs. So the sorting of fx1, fxn is fi1, fy2, fi. Well, the reason is very simple, of course. If you apply comparators in such a sorting network, then the comparator does not know about the absolute difference between two elements that are compared. It only knows that one is larger than another. So, for a comparator network, this relation between input elements counts. And that applies that the decision made for xy and xj does not differ from the decision made for fxy and fxj. So if you achieve this output for x1, x2 until xn, then the same path in the computation, of course, are taken for fx1 to fxn. Okay, so the lemma effect says that sorting is not affected, does not change by monotonically non-decreasing transformations of your input. And it's a simple lemma that we will need. Because now we will deal with the original theorem. A sorting network S with n inputs sorts every input vector correctly, if and only if S sorts all 2 to the power n binary input vectors correctly. And well, this is one of the proofs that I would like to go through with you, because it's a very instructive one, and we need to apply the theorem after all to some particular cases. So, well, let's just go through the proof. So the proof has two ways. So you can assume that this is true and then prove that the second half is true, and you have to show that if the second half is true, the first half is also true. Well, it's of course always the case that if you sort every input correctly, and inputs correctly, then of course you sort also binary inputs correctly. And so the first half, assuming this and then to follow that, that's trivial. The hard case is of course the reverse. Assume that you sort all 2 to the power n binary vectors correctly. How to show that indeed all inputs are sorted correctly? Well, there is one famous technique, of course, in such proofs, and that's if you would like to prove something, then just assume the converse and show that it doesn't hold. Then you are forced to assume the original. So, assume now that while all binary vectors are sorted correctly, the sorting network makes it a mistake with some arbitrary input. So we have some arbitrary input, x1 to xn. We observe an output, y1, y2, yn, in increasing order, hopefully. And now it appears that for some given I, we have yi is larger than yi plus 1. So there is a mistake. And now we show that if such a mistake occurs, it would imply that
already makes an error in binary factors. So that would imply that our assumption does not hold. Okay. So, to prove that now we arrive at a contradiction, we make a function, f. And this function has some domain, let's say natural numbers or integers or reals or whatever. It's an arbitrary domain. It's ordered. And it maps such arbitrary numbers to binary numbers. Right? And it's defined as follows. As long as you have here an x that is smaller than yi, then it's mapped to 0 and it's mapped to 1 else. Right? So here you have the critical point, yi. Okay. You should note immediately that f is monotonically non-decreasing. Yeah? That simply follows here from the definition. Right? All numbers, that if you have two numbers, x1 and x2, and x1 is smaller or equal to x2, then the f of x1 cannot be larger than the f of x2. Yeah? By means of this definition. Okay, so we might be able to apply the lemma that we discussed before. Now, given x1 and x2 and xn, we can also consider fx1, fx2 and fx. Note that since f maps an arbitrary number to a binary number, these numbers are all 0, 1. So we have a 0, 1 vector. So according to our assumption, S sorts all binary vectors correctly, we should have that the S of this binary vector gives you a binary vector f y I1, I2, n that is sorted correctly. So we should have the f of I1 is less than or equal to the f of I2, less than or equal to the f of In. So in other words, this should be either a vector that's entirely consisting of ones, or should start with a number of zeros and then finally ones. Then we have a sorted variant. Okay. Now we will show that this cannot happen. In other words, we already made a mistake here with sorting the binary inputs. Why? Well, look at the f of yi. It should be equal to 1. Why? Well, we defined if you have an input x here, or yi, then it should be 0 if x is less than yi, and it should be 1 else. So fyi is by definition equal to 1. But fyi plus 1 is 0 because yi plus 1 is less than yi. There was a mistake. But that means that now in this vector, this sorted vector, we have a 1 appearing before a 0. So our assumption that S sorts all 0, 1 vectors correctly now is contradicted. Of course. Why was it contradicted? Well, because we assumed that in making in applying the sorted network on an arbitrary vector, we would make an error. So this shows that if you assume that all 0, 1 vectors are sorted correctly, then you have to sort all input vectors correctly. So we end with the conclusion that indeed, from the assumption that all binary input vectors are sorted correctly, you can arrive at the conclusion that all input vectors are sorted correctly. And this is a very famous principle. It was invented 70 years ago on a very on a completely other domain, but it can help you enormously in proving some of these more complicated networks to be correct. And I will show you in a minute how we can apply it. We will apply this theorem to a rather complicated merging network. And the idea is that by giving this proof, I can show you how easy it is to apply this principle to a rather complicated network that, well, maybe without the help of this 0-1 principle was not amenable to analyze as being correct. What's the idea here? What we would like to do is the following. We would like to invent a network that's capable of taking two sorted inputs and merging them to one sorted sequence. So we have two groups of n inputs, x and y. And we have as output a group of two n numbers. And if x and y are sorted, then z equals the sorted combination or the sorted merge of x and y. Okay, so here is our network. Here we have the two sorted inputs, x and y, and we have a network that's capable of dealing with two n inputs and two n outputs, and it produces a merged output. Okay. And now we apply the same principle as before. We try to imagine that we know how, for example, an Fn network looks like, and we build from this assumption an F2n network. And that's rather complicated in this case. So here I have n sorted inputs, x1 to xn, y1 to y. And now I take two networks that are capable of dealing with n inputs, fn and here another n. And now I distribute my inputs over these two networks. So the odd inputs are given as input to Fn as the first n divided by 2 inputs of Fn. So x1, x3, xn minus 1 are fed to the first Fn, and the even inputs x2, x4 and xn are fed to the second merging. And for the second input, the same happens. So the odd inputs are fed to the corresponding network, y1, y3, yn minus 1, and the even ones are fed to the first merging network and the second positions. So each of these networks receives half of the inputs, the original input factors. Then we consider the outputs of them, and these outputs now are pairwise compared. So the first output of the first network is compared with the first output of the second network, and the minimum of them appears at the first output, so it's the minimum of the total input. Then the second one, then the second is compared with the second of these, and here this is the third in size, the fourth in size, fifth in size, sixth in size, and here the final maximum of the total absorbed input appears. Just by making these comparisons. Okay. This last network, subnetwork, is known as a perfect shuffle, and this is this part of the network is known as an odd even merge network, sorry. Yeah. That's an odd even merge network. And from this network now we can derive, of course, in the same way as we did with insertion sorting networks, the two parameters that determine the amount of hardware and the amount the amount of time. So, well, take a look at this network, and now you see that, well, in fact, what we need to do to build such a network is two of those subnetworks that contain comparators of their own, and then, of course, here n of those comparators we have to add. So, the size of the network is 2 times the size of Fn plus n, and the size of Fn, F1, we can simply put to 1. So what's the outcome? The size of Fn is the O of n log. The depth of F2n is the depth of Fn plus 1. If you take an arbitrary output path, you see that it touches one of those comparators. And that means that the depth of Fn is the O of log n. So this means that compared to insertion sort, this merging is quite cheap. For the insertion sort, we already knew that the size is n squared. Here we have n log n. Okay, but the main problem here is to prove the correctness of the network. So why would this network be correct? Why do you trust it? Well, use the 0-1 principle and just show that this network is correct for all binary inputs. And I will give you a rough proof of the correctness of this network. So, concentrate on binary inputs. Yeah? How do these binary inputs look like with respect to the two input vectors x and y? Well, assume that x has r zeros, well, y has s zeros. Then the output u1, u2 of un of the first Fn network, so this was the output of the first Fn network that we saw just before, consists of this number of zeros followed by ones. And you have to look here at the floor and the ceiling that differ. Yeah? Because the first inputs appear in this first network that are derived from the odd positions of the first vector, then the ceiling of the first half of the zeros that came to this network have to be counted, and the floor of the remaining ones have to be counted. Let's just look at look, here assume that you have r zeros here. Yeah. That means that half of them will go to the first network and half of them will go to the second network. Yeah. But, of course, depending upon this number r, the ceiling of r divided by 2 go to the first network, and the floor of r divided by 2 go to the second network. Because you start here with the first 0. And the same holds, of course, for y1 until yn. So if you have s zeros in y, then, well, s divided by 2 and the ceiling of that goes to the second network, and the floor of the first r are going to the second network. So there is a slight difference between this ceiling and the floor. And here you see it. Floor, the ceiling and floor. And the same holds for the second output. Here the ceiling and here the floor. And now the basics of the proof, and I will continue after the break, is the following: that we have to take care for, well, the effect of rounding here on S and R, because that might imply a difference. So if, for example, R and S are both even, then it's very simple, because then this number equals that number. And what's the significance of comparing an equal number of zeros and an equal number then of course of ones? That is that in the resulting network, if you take these comparators, then at the input lines of these comparators there is always appearing a zero, both zeros or both ones. So there is no difference. There is no comparator that receives a 0 and a 1. Okay, we will continue after the break by distinguishing these cases.